All right. It's a new day.
It's pretty sunny outside.
Yes. It's a nice day for November. All right, couple more people maybe? Lucy seems lifelike now.
Just barely. Still not light out yet.
Yeah, all right. All right, I think Brielle was here. Let's see if she makes it back. We'll try again. So I thought that we'd talk about treatment effect models today and show you some treatment effect models on Friday, and then Wednesday I'm going to bring cupcakes. All right, Brielle's almost here. Brielle, you there? Hello, Brielle.
Hello.
You are now. Good. All right. All right.
Wonderful.
So let me try again. So where we were, I was talking about treatment effects models, where there's some sort of a treatment, often a policy, and we want to try to be able to evaluate the effect of the policy. And so, all right, I'm gonna pin this. Okay. So the problem that we're going to focus on is often referred to as the evaluation problem. And the evaluation problem goes like this. There's some sort of an intervention that we want to be able to analyze, to figure out the effect of. And so let's suppose that the intervention is putting textbooks in some schools, and we want to know how does that affect performance in those schools, okay? And by the way, these sorts of models have become really popular in the past, I don't know, 15 years, excuse me, or so. And there was a Nobel Prize awarded last year, I think, to Esther Duflo and some other folks at MIT who have really made these models popular, particularly in development economics, as applied to developing countries, where people want to try to figure out the effects of various kinds of interventions to see where it makes sense to try to spend money and where it's not useful. So suppose the intervention we're interested in is providing textbooks to schools. And the outcome that we're interested in is maybe performance on a test, maybe a standardized test. So let performance on the test be y. Okay. And let's do this. We'll say let y t I be the average score on the test for students in school I with textbooks and so T represents a treatment. Textbooks are the treatment in this case. And let YIC be the average score on the test for students in school I without textbooks. And so C is the control group. And so the idea is that we'd like to measure YIT minus YIC which is the effect of the treatment but there's a problem. And the problem is that the schools that get textbooks don't not get textbooks, and the schools that don't get textbooks don't get textbooks. And so we can never compare a school with and without textbooks. Each school either gets the textbooks or doesn't, and so that direct comparison is not really available. Right? So if you think about the Andrew Yang policy, where everybody gets $1,000, we decided to do an experiment. We give some people $1,000 and some people not. And we want to compare them. Well, the people who got $1,000 got the $1,000, and the people who didn't, and they're different people. And so we can't really observe this thing. Perhaps instead, we can observe, and by the way, this is fundamentally the evaluation problem. We want to do an evaluation, but it's just not physically possible to do it directly. And so at this point, we have to try to be clever to come up with ways to do it. Difference in difference estimation was one approach that we looked at. And we'll talk about exactly when that fits and when it doesn't, but there are other approaches as well. So perhaps instead of observing this, we can instead observe the expected value of YIT minus YIC. The average effect. So this is the average treatment effect. And maybe there's some way we can find the expected value of that difference, even though we can't observe the difference directly. Right? So suppose we have data on many schools. And some of the schools get the treatment and some don't. So some are treatment and some are control. In that case, we can group together the treatments and group together the controls, and we can find the expected value, or just the mean, of the test score for the treatment group, given that they got the treatment. So just limiting ourselves to the treatment group, we can find the expected value of the score for that group and subtract from it the expected value of the score for schools in the control group. And we could just call this the difference. Okay, so this is observable. We just take all the treatment schools, find their mean, take all the control schools, find their mean, and look at the difference between the two. But we want to be careful about this because this computation can be misleading. And to show you why, or how it could be misleading, we'll do a little, a standard econometric trick, which is this. We will add and subtract the expected value of yi for people who don't get treatment from the treatment group. So these are people in the treatment group who don't get the treatment. We'll add and subtract that from this. And so D then becomes the expected value of y I t, given that they're in the treatment group. So the expected value of people who are treated from the treatment group minus the expected value of people who are not treated from the treatment group minus the expected value of y I c, people who are not treated from the control group, plus the expected value of people who are not treated from the treatment group. All right, so all I've done is to take this term and I subtracted it and added it. Okay. And now I can rewrite this. These are both within the treatment group. And so I can combine those two terms as yi treatment minus yi control from within the treatment group minus the expected value of yi from the control.
Professor?
Let me just finish writing this now.
Okay.
Yeah,
Could you just move up a bit? Okay, perfect.
sorry about that, yeah.
So just to clarify, what you're adding and subtracting are like the chance that you have a school that you have put in your control group, but it turns out that it does have textbooks.
This group,
Well,
This-
you were saying like, yeah, like, so you add and subtract people.
so
that
this is a group that's in the treatment group, but doesn't have textbooks. Okay, so essentially this group is in the pre-treatment state. Okay. So this thing is, this has a name. This is the treatment effect on the treated. This is the thing we'd really like to be able to observe. Okay, so this says if we just take the treatment people and we look at the effect, their expected value after the treatment versus before the treatment, this is the effect of the treatment. Okay. But what's this thing? So this is people who are untreated from the control group and people who are untreated from the treatment group. And this is the difference between those two, right? It's this minus that. Really, I could flip that around and you would see that difference. This is the magnitude, magnitude of selection bias. Okay, so what is selection bias? Selection bias is when you take a sample, you want to compare two different groups, but the groups are not assigned randomly. So in this case, suppose you have the control group and the treatment group. And if the control group happens to be outlying areas in this developing country, and the treatment group happens to be all places that are in urban areas, that's very non-random. And you'd expect that there's probably some sort of a difference between them even without the treatment. Okay, and so the way that you have selected your sample then leads to this bias. So selection bias is a thing that comes up in a lot of different contexts. If you compare the earnings of women with children and women without children, it's not a random assignment between the two groups. And you're likely to find there are systematic differences between them. And if you don't account for what causes that difference in the two groups, you will have biased estimates of selection bias. Selection bias comes up a lot in story of the day medical reports. So the story of the day medical report is that people who walk 10,000 steps per day are healthier than people who don't. Well, is that the only difference between those people? Chances are pretty good that the people who walk 10,000 steps per day have a variety of things that are different than the people who don't. And just attributing the difference in health outcomes to the steps is a mistake. Okay, and so sometimes we misattribute differences because the people who are assigned to our comparison groups are not assigned randomly. So what this selection bias term in this case is saying is, this term is saying that if we compare the two groups before the treatment, are they different before the treatment or not? If they are different, then this difference between them is going to bias our estimate of the treatment effect. If they are not different, then we can go right ahead and just, we're going to be left with this. If they're not different, this becomes 0. And the treatment effect that we're computing is going to be fine. But if they are different, then we need to do something to to account for that difference.
Professor?
Yeah.
I have a question. Can't we avoid this kind of selection bias if we just compare before and after, like same schools before textbook with after textbook?
Well, so after the textbook is introduced, are we assuming that nothing else has changed?
Yes. I mean,
You
I
have
think
to make that assumption, right?
yes.
You have to make that assumption.
Mm.
So maybe you can do that. Think back to the difference in difference estimation we did.
Mm-hmm.
Right, so what we did in that case was we observed some sort of a policy change, and we looked at before and after the policy change, and we're assuming that the only thing that really matters is the policy change. We control for a bunch of other stuff in our regression, but we're assuming that after we've done that, the only thing that changes over time is the policy.
Mm-hmm.
And that may be a good assumption, it may not. What we saw in the case that we did with the traffic fatalities,
Mm-hmm.
what you had was a situation where you say, well, there's a change in the law, but it seems like there could be a lot of things going on,
Mm-hmm.
right? And you're left with this estimate that kind of shows something, but you're not really convinced that you're showing what you set out to show. And so that's a problem with that kind of approach, the before and after. And let's talk about what the approaches are that people use for trying to get at this, to eliminate the sample selection bias. Let's see. So potential solutions. I'm going to focus here. Focus. Focus. Sooner or later it'll focus. Come on. All right. Boy, I wish I could do this approach to teaching forever. It's just great. Oh, man. Anybody know any jokes? No jokes. All right. So one possibility is randomized evaluation. Try again. Still nothing. That's focused. Boom. All right. Found it.
looks like
So,
magic.
one possibility is randomized evaluations. So in this case, you say, suppose N schools are selected, and then assigned randomly to treatment or control group. So the randomness is the key detail here. And because the assignment is random, the expected value of yi to control the treatment, so that's the pre-treatment treatment group, minus expected value of the untreated control group. That's expected to be 0. So the expected value of y for the treatment group minus the expected value of y for the control group is the expected value of yit minus yic, which is the thing that we're looking for. And so random assignment is one way to eliminate the selection bias. One reason that these methods have been really popular in developing countries is because social scientists, particularly economists, come up with little experiments to do, like putting textbooks in some schools and not in others. And in developing countries, they can actually do these experiments relatively cheaply, and people will allow them to do the experiments. What are the problems with this approach? One is the cost. It can be expensive to carry out an experiment like this, particularly if you need to measure a bunch of outcomes and a bunch of characteristics. Second, there are often ethical issues. So just suppose you're working on a treatment for a virus, okay? And what you want to do is, what we'd like to do is to get a whole bunch of people who are willing to be part of an experiment and randomly assign some to the treatment and some to the control group. The issue is, one, if the treatment is actually useful, putting people in the control group doesn't seem like a nice thing. Two, the treatment may in fact be harmful, and getting people, subjecting people to a harmful treatment isn't such a great thing. And so essentially what you're doing is you're experimenting on people. One place where this comes up a lot is, and I've heard this recently, where people have been talking about various potential treatments for a coronavirus. They'll talk about various treatments, and then say, but we don't know what the effect is on pregnant women. Well, why don't they know what the effect is? Because nobody wants to do experiments on pregnant women, right? If you take a group of pregnant women and you assign some to the control group and some to the treatment group, nobody really wants to be in either group, right? You don't want to be experimented on when you're pregnant. And so, and that ethical issue, that issue is really insurmountable for some groups, like that group in particular. And the third issue that comes up with randomized evaluation is the question about external validity. Is the sample representative of the population? Right? Can we take the results of an experiment done on a sample and be sure that they will apply to the population? The easiest way to think about this, I think, is, again, if you think about drug trials, who are drug trials done on most often? Rats. Okay, and so what happens is you do a trial on rats, you put some in the control group and some in the treatment group. The rats don't complain either way. You figure out that the treatment is effective on rats, and now the question is, well, who else is it going to be effective on? Is it going to be effective on humans? We don't know. And at that point, we sometimes run into a problem. So for most people who do this kind of thing, randomized trials are the sort of the gold standard. If you can carry one out, if you can actually get one arranged, set it up, carry it out, it's the cleanest thing you can do. Because of the fact that you can assign people to groups randomly, it's just completely unconfounded. But it can be difficult and it can be costly. And again, it's not surprising that Western economists end up in developing countries carrying out these experiments because it's just easier for them to actually get access there. So that's one way to get at this. That's the first choice if you can do it. The second possibility would be to use regression. And so you might think about estimating some model like yi is beta naught plus beta 1t for the treatment plus beta 2, x2, et cetera, all the way up to beta k xk plus epsilon. And so you might do that. And this is really pretty close to what we did in difference in difference estimation, where we had this interaction variable, which really stood for treatment, and it allowed us to see what the effect of the treatment was. Okay. So if you have enough data, that's not bad. But there, again, are potential problems with this approach. One problem is you're likely to have some sort of an omitted variable bias. Right, if you collect data, chances are pretty good you're not going to be able to collect absolutely everything that you'd like. And so maybe you would be tempted to use some sort of like a fixed effect model to do this. Now you need at least 2 observations on everybody. And so the data costs can become difficult, can become prohibitive. And a second important problem is, again, selection bias. Because we have no guarantee that people were assigned to the treatment randomly. Okay. But that's an approach you might consider, is regression. Let me just go back to one section. And regression really falls under a larger category, which is estimation based on observable. Real, I think it's for you. I like the way Braille only unmutes to laugh.
Ah,
All right. So selection, estimation based on observables. So in regression, we're assuming that we can observe everything that needs to be observed. And that's why we do the regression. The problem is there may be certain things we actually can't observe, and we may have some selection bias. Another case in which we have observables, a third method, is what's called matching. And here's where stuff starts to get interesting. So again, we're assuming that we can observe everything we might want to observe about these the people who are subjected to this treatment. Okay. So so for matching, first you define all characteristics of all people, schools, whatever the unit of observation is, of all people in both the treatment and control groups. Okay, and so if we're talking about individuals, we know everybody's age, sex, marital status, number of children, income, everything you could think of that you might want to observe about them. And now you can pair all observations with identical characteristics. And compare their outcomes when they're in the treatment versus the control. Okay, so we take our entire class and we want to find people who are subject to the treatment and people who are subject to the control. And we want to pair up people in those two groups. Okay, and so we identify that there's someone in the group who's part of the control, and they're reasonably good at squash. And they're male and from Malaysia, and so we pair them up with Andrew, who got the treatment. Okay, and now we compare, since we've basically taken all the other things into account, we simply compare those two people. And we do that, we match up everybody in the sample with someone who's identical to them without taking the treatment into account, and then we see how the treatment affects them. Okay? This sounds crazy, yes? So this is matching, and people try to do this. And if you have a very large sample, there's software that will do this for you. You say to the software, I want to match people on the following 8 characteristics. And everybody who matches on those characteristics, pair them up. And the ones who get the treatment, let's find the expected value for them. And the ones who don't get the treatment, we'll find the expected value for them. And from that, we get the treatment effect. That requires a lot of data, a lot of information. In principle, it makes sense. In reality, it's pretty hard to do. So what do we do? Because it's difficult to do this, we have a fallback position. And the fallback is this. Instead of doing matching, we do propensity score matching. And so with propensity score matching, rather than literally matching people up one-to-one, we look at people's characteristics, and based on their characteristics, we give them a propensity score. So the propensity score equals the probability that they'll be in the treatment group. And so we look at all their characteristics, and based on that, we estimate the probability that they'll be in the treatment group. And so even though your exact characteristics might not match up exactly, if you have a probability of 0.23 and someone else has a probability of 0.23, then we'll compare you. Okay? And so now we compare members of the treatment group with members of the control group who have the same propensity score. I put same in quotation because it becomes a judgment about exactly what it means to have the same propensity score. So your propensity is 0.23156 and my propensity is 0.23158. Is that the same or is that different? And so it turns out that there are a number of different ways of figuring out who's comparable. So one way is to say, I'm going to take the propensity score, and anybody who's within 1/10 of a point of each other, we'll consider them the same and we'll compare them. And there are a variety of ways to do this. Lucy.
So the propensity score is the probability that they'll be in the treatment group. But if a lot of people have similar propensity scores, wouldn't it be hard to find people that have similar scores that are in different groups? Or is that?
It may be. It may be. And And it turns out that actually doing this estimation is sometimes made very difficult because you don't have a good sample that does what you want it to do. That's life in econometrics, right? You can see what you're trying to do here. And the question is whether it actually works. And it turns out that when you do this, there are a number of sort of checks that you have to do to make sure that the data are actually appropriate for this kind of comparison.
Okay, because to me, I feel like if you have a propensity score where you have two people that are like 0.7, it's more than likely they'll both be in the treatment group. So,
Well, but that's the idea. I mean, is that the propensities may be the same, but think about if it were random treatment, whatever the propensity is, they may be assigned randomly to different groups, and they don't necessarily have control over that. Okay. And so the basic idea is we're trying to find people who are fundamentally similar and comparing them, which is easier than the straight matching where we have to find people who are identical. Okay, and so essentially we're matching people based on sort of an index instead of matching them exactly on their characteristics. It's just more doable. It's difficult in both cases, but it's more doable with the propensity score. Hannah.
But like, let's say that like two people have the same propensity score. How do we determine which one goes into the control, which one goes into treatment?
That's been determined before they, when we collected the data, we're going to see that some people live in a place that's subject to a policy and some people are not subject to the policy. That's part of the data collection, right? Well, our hope is that that's independent of being placed into the group.
So beforehand, we will say that these people, like our people coming from this region or whatever, are going to be control, and these people are going to be treatment, and then we calculate the probability of them being treatment and compare it. That's what we're doing?
Right. So I wrote a paper once where I was interested in how a person's, it's labor economics, so it's people at work in their jobs, how the gender of your supervisor affects your pay. Mm-hmm. And so the question is supervisor's gender assigned randomly or not? It's hard to know, right? It may be that if you're a woman, you're more likely to be assigned to a female supervisor. Andrew, are you, Andrew? Noise? Thank you. And so what I did in this paper was to do propensity score matching. And so I looked at the propensity to have a female supervisor, and then looked at, for people with a similar propensity, was the supervisor actually female or male? And some have female supervisors, some have male supervisors. And we could then compare the difference in their earnings based on whether the supervisor was actually male or female. So you have to assume at some point that there's some sort of a random component to that assignment. But, I mean, so what's interesting to me about this is the evaluation problem is pretty easy to explain what it is. But actually computing it, you can see, turns out to be complicated and kind of fraught with all these difficulties. And particularly when you're using really micro data, it's challenging. Anybody else?
What's the result?
What was the result?
Yeah.
I can't remember. Actually, you know what? I looked at this paper just the other day because let me see if I can find it. See if it's still here. Here we go. Hold on. This paper uses data, blah, 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 about women associated with working for female supervisors. we find that estimates, when using ordinary least squares, we find estimates of supervisor gender effect similar to those in existing literature, whatever that is. However, when using fixed effects, we find no evidence, and we conclude that OLS estimates overstate the importance of the impact of supervisor gender on wages. So basically, I think we found that there wasn't much of an effect. I'd be happy to send that to you if you would like to. If you're having trouble sleeping during these troubled times, maybe you'd find it useful. All right. All right. And there's one more approach that I'll mention. And that approach is difference in difference estimation. Okay. And so that's the approach of using, when we did this, we talked about the idea of natural experiments. And so natural experiments are these things that happen not because some social scientist went out and did an experiment, but because somebody changed a policy and gave us the opportunity to look at the before and after effects of the policy. So we've already done difference in difference estimation. And what I want to do is to basically, I think on Friday, what we'll do is we'll look a little bit at propensity score matching, because it's kind of fun. And there's also, we can do the regression approach too, because Stata makes it easy for us to do that. And maybe we'll get a better feel for exactly what this looks like and how it works. Okay. Have you been educated today? Excellent. It's my job. All right. I will stop there. Anybody have anything else to talk about? Any questions? So if you have any questions about this, we're happy to talk on Friday, or I'll give you some examples on Friday. If you have anything you want to talk about with respect to the last lab, let me know. And otherwise, try not to make your life more complicated than necessary. Okay. All right. All right. So take care of yourselves, and I will see you Friday, and let me know if you have any questions about anything. All right.
Thank you.
Thank you, Professor.
Bye.
Bye.
Bye.